Okay, this is a video that contains some things you need to know about logs. So we already know some things about logs. We've spent some time talking about some of their properties, like the or their rules, the product rule, the quotient rule, the power rule, but there's other things just in general that you need to know about logs. So when we've got something like log base b of a number equals some other number, there are a couple things that you need to know here. One is that b must be greater than 0. All right. There are some really weird and bad things that can happen if you let b equal 0 or if you let b be less than 0. So it can't be equal, it can't be less than. Let me just give you one example of many. So for example, let's say we put -2 in here and we put 8 and we said, what is this equal to? All right, well, we already know that we can convert any log into an exponential function, and so if we do that, then this right here, which is the base of the log, would become the base of our exponential function, and these two essentially flip-flop. So here the x acts as the exponent on the -2, and the 8 becomes the answer that we're looking for. So then I'm asking the question, -2 to what power equals 8? Well, you might say, oh, I recognize that 2 to the 3rd power is 8, but then we get this. -2 to the 3rd power is actually equal to -8, not +8. There is no number that I can fill in here where I'm going to end up getting a +8. Because if I put in any other number that would make it 8, actually the only number that would make it 8 is 3, but then I'm going to end up with a -8. So we just would not have a solution to this, right? So that's just one example, and it has to do with the fact that a negative times a negative is a positive, but then if you have 3 negatives together, then you end up with a negative here. So it messes things up. So we're just going to say for right now, actually forever, that the base must always be greater than 0. It can't be equal to 0. It can't be less than 0. All right, so one thing that we can say is b must be greater than 0. All right, the second thing that we can say is that you can't take the log of 0 or a negative number. All right, let's try taking log of 0 first. So let's say we have log base 2 of 0 equals some number. I'm choosing 2 here because we're familiar with the powers of 2, so let's just rewrite this in exponential form. This says 2 to some number equals 0. Again, I leave this as the base. It was the base in my log, it's the base in exponential, then I flip the two of these around. So I get 2 to what power equals 0? Well, nothing. You might say, well, how about 2 to the 0? But 2 to the 0 equals 1, not 0. Right, there is no number of times that I can multiply 2 together and get 0. It just doesn't work. All right, so I can't take log of 0. The second one is I can't take log of a negative number. So let's say I had log base 2 of -2 equals some number. So that's saying 2 to what power equals -2? Well, again, there is no way I can multiply only positive numbers together and get a negative number. All right, so that just doesn't work. We can't take the log of 0 or a negative number. All right, so let's put this as 1. Let's put this as 2. The conclusion that we can make, or a deduction that we can make from this, is that I now have a restricted domain. The domain of logs is not all real numbers. All right, why is that important to know? First of all, it affects what we can put into the function, because the domain is all the x values that we're allowed to put in. Again, I have x written on the wrong spot here, but it's anything that we would put in here. So the domain is restricted. That means, here's the next one, that you must check for extraneous solutions. right? We've run across two other functions like that so far. That would be any square root equation. So again, if I have, I don't know, square root of x squared minus 3 equals, I don't know, 37, that we would solve that, and whatever values we got for x, we would have to then plug it back into the original equation, because there are certain things that we're not allowed to put under the square root here. We cannot make this x squared minus 3 negative. If we do, we'd be taking square root of a negative number, which is not possible in the real number system. So we can't take, we have to check for extraneous solutions with square roots. We also have to check for extraneous solutions when we have rational equations. So let's say we've got 5x over x plus 7 minus 6x over x squared minus 5 equals 2. If we had an equation like that, whatever we got as our solution, we would have to plug it back in to make sure it didn't make the denominator 0, because that's a problem. We can't have 0 in the denominator. So the reason that we end up checking for extraneous solutions is because the domain is not all real numbers. So because the domain of logs is not all real numbers, I can't take the log of 0 or negative numbers. That puts it in this category. So now we have to add to our list of types of equations where you have to check for extraneous solutions any square roots, any rational equations, and any log equations. So we've now added a third thing to that list. Okay, that's all, actually, and then the next one is going to come out of the blue here, and that is that logs, and I'm going to also put exponentials in here, logs and exponentials functions are 1-to-1, and that is abbreviated 1-1. So this is the shorthand notation for it, but it's read the same way, 1-to-1, 1-to-1. Okay, you might be thinking, what the heck is that? So let me explain a little bit further. All right, so we know about functions. A function is a rule that says that for each x in the domain, there is a unique y in the codomain. Right, we could also say potentially range if we had restricted that enough, right? So that's the definition of a function. Logarithms and exponentials are both functions, right? Again, we learned about that, the horizontal line test, which said that if I take any function, so I'm just going to graph an exponential right here, and I draw, no, I didn't, sorry, I meant to say vertical line test. If I draw a vertical line through it anywhere, it only hits the graph one time, all right, at most one time. All right, so we already know that an exponential is a function. We have not yet graphed any logarithms, but here's what they look like as a rule. All right, so if I draw a vertical line anywhere, it only hits it one time. All right, so they're both functions. I realize that it looks a little dicey down here, but it's constantly moving closer and closer to the y-axis right here. So anywhere we draw a vertical line here, it's only going to hit it once. And if it doesn't, it's my bad drawing, not the function that's the problem. All right, so 1-to-1 is an adjective that describes a function. All right, so if we don't have a function, we can't possibly call it 1-to-1. It's only an adjective that describes certain functions. All right, so instead of a, let's say certain functions. All right. So in order to be one-to-one, first of all, you have to be a function, but second of all, you have to have this property that for any y value in the range, right? So one-to-one means that for any y value in the range, again, range, we're looking at all the possible y values. How far does it spread up or down? So for any y value in the range, there is only one x value that matches to it. All right, let's look at some things, some one-to-one functions that we know and some functions that are not one-to-one. So here's our favorite one-to-one function, something that's linear, right? If I pick any y value in the range and I go over here and I say, oh, there was only one x value that created that, right? I can do that to any y value in the range and I'm only going to come back to one x value, right? Exponentials and logarithms do that, right? Where if I take any y value in the range and I go over, I come down here, there's only one x value that created it. Same thing here. If I pick any y value in the range, there's only one x value that created it. Let me give you some examples of other functions that we have looked at that are not one-to-one. So for example, we've looked at absolute value graphs. All right, so for example, let's say I say this right here. Well, this x value created it, but so did this one right here. All right, so let's say this is x1 and this is x2. There are two different values that give us that same, two different x values that give us that same y value. Right, so this is not one-to-one. Here's another example of a function that's not one-to-one. We haven't graphed any of these yet, at least not to a great degree, but this is a quadratic, right? So again, I pick any y value in the range and I say, okay, that y value or that x value down here created it, but also this x value over here created it, right? So this is also not one-to-one. Right. There is a test that you can do that will tell you whether a function is one-to-one without having to do a lot of work, and that's called the horizontal line test. If I can draw a horizontal line test anywhere through the function, sorry, let me bring that back here, and it only hits once, then it's a one-to-one function. So we can see that with logarithms, they are one-to-one. We can see with exponentials that they are one-to-one. We can see with linear equations, they are one-to-one because no matter where I draw that horizontal line, it's going to hit the graph only once. We can see that with absolute values, no, it doesn't work. When I draw these lines, they hit it multiple times, right? Same thing with quadratics, right? They're going to hit in more than one spot, right? So the property that we need to know for the next thing that we're going to do is that logs and exponentials are one-to-one. All right, so that is all I want to say right now about things that you should know about logs. And I will see you in the next video.